first talk of today. It's a keynote speaker, Greg Matloff, Starflight review. Greg is a leading expert in propulsion for interstellar travel possibilities, especially near sun solar sails trajectories that might ultimately enable interstellar travel. He's a tenured astronomer professor with the physics department in New York City College. And so he'll be our first speaker of this morning. So let's all welcome him.
Well, good morning, everybody. It's a pleasure to be here. And very interesting to note the change in weather outside, which wasn't supposed to happen, but we have to live with it. Anyway, what I decided to do with this keynote is to give a review. And the review is what's going on with interstellar travel, where we've been, and where we might go. I've been doing this work for a long time. As many people here realize, I did the Starflight handbook with Gene Malov. I knew Bob Forward. How many people here knew Bob Forward? It's a fan number. How many knew Gene Malov? One. See, okay. And this gives a little bit of my background. Doesn't mention the Starflight handbook or deep space probes, but that's okay. Here's an outline of the talk. What are we doing? Why are we doing it? What are the obstacles? Can we overcome them? What are the feasible modes of Starflight? And then there's the possibility. Some people in this field don't think humans will ever do it. Like Frank Tipler, Phil Lubin, Lou Friedman. People like this are quite certain that our type of human being will never do it. But we may not remain our type of human being. So space travel might have to, interstellar travel at least, might have to consider transhumanity. And finally, I'm going to talk a bit about the wildcards, about the breakthrough concepts, which don't seem to have, many of them, a real physical background, a theoretical background, but there are anomalies. And I think we have to be fair and treat them because, like many people here, I would love to see a human diaspora into the galaxy. And I would love to see human beings reaching the point where they can play a real role in the future development of consciousness in the universe. We'll continue. Okay, these are the possible reasons to go to the stars. One of them, of course, is adventure. You look back at the space operas of the 1920s and 1930s, and what you see in this constantly is we go to adventure. Somebody develops a space drive in their basement, which would be a lovely thing to do. And somebody like Jean-Luc Picard stands at the bridge of a starship and says, let's see what's out there. And you go out to see what's out there. It would be wonderful if we could do it. The problem is, with any conceivable space drive today, you'd be taking a very long, boring time to get to your exciting adventure. How about imperialism? We look at Star Wars, things like that. Look at the Borg on Star Trek. Might you wish to take over the entire universe? That would be a little difficult, since modes of projecting humans across the galaxy are maybe 1,000 years to get 4 light years. You have to have a very dedicated Napoleon or Hitler or somebody with the yellow wig, a very, very dedicated individual like this who would do that. And man, that type of dedication you're probably not going to find in a megalomaniac. So, okay, what I think the only way to do it is species survival or biosphere spread. I remember in 1970s the concept of Gaia, an integrated human biosphere, developed in synergy with Jerry O'Neill's space colony ideas, and the two were feeding each other. And I think that's definitely going to be the case. Finally, what is the role for technologically advanced conscious life? Lately, as some of you might know, I've been playing around with various aspects of universal consciousness, or what the philosophers call panpsychism, to see if there are astronomical evidence for this thing that we can measure. And it would be nice to think that not only is the universe conscious, but is there a role for our type of consciousness, which is technologically conscious. There are many intelligent species on this planet, probably 6 or 7 or 8 or maybe more than that. There might have been others that lived in the past. There is only one that can modify its environment as we've done, and that's us. Okay, we have a number of obstacles which we have to overcome. The first is the size of the universe. And these are just some examples of it, and this is the type of thing I give to my students in the astronomy courses that I still teach, even though I did early retirement. I came back as an adjunct. How many people here are full-time faculty members? It's much nicer to be an adjunct. You avoid all the politics, and it's particularly nice after you have the pension, so it's great. Okay, then you have both. You avoid the politics, and you've got the money, so that's good. Okay, and basically we know that to get to the Earth's moon at 240,000 miles or so, and I'm sorry if I jump back and forth for miles and kilometers here, because I'm used to using kilometers, but I realized I was giving a talk in the US where many people like to use miles. So I'll jump around. And you can see that the universe is a rather big place. To get to Mars at its closest, that's around almost 200 times the distance to the moon, which is one reason why humans haven't flown to Mars right now. We have been above the Earth magnetosphere for a maximum of about a week, 2 weeks. No big deal in terms of cosmic rays, but you do it for the length of time you have to use to go to Mars, and astronauts might come back brain dead, which most of them don't want to do. Okay. All right, let's continue on from this. And this, of course, is a very famous map, which I initially had thought was generated at Marshall. It actually, I believe, comes from JPL. My first year consulting for Les Johnson in 1999, he had me go over this. I believe it had been issued in 98 or 99. And I love it because it makes things look so small and manageable. And Mark Millis has something up on the wall back there near breakfast, which is more linear, not quite as manageable, but maybe more realistic. I love it. Okay, we'll continue. Now, we also have temporal issues as well as distance. Distance and time are related. Using the technology we have today, you can make a round trip to the moon in approximately 2 weeks using the same propulsion technologies. And these are not just chemical, but nuclear or solar. The round trip to Mars is between 1.5 and 3 years, typically. And if you apply giant planet gravity assist, you can get from the Earth to Neptune in about a decade. The same probe will get you to the nearest star in about 60,000 years. Now, if you take a near-term solar sail, and this is something I did for Les on one of the summers I was there, you take a near-term solar sail as optimum as you can make it, and you apply also giant planet gravity assist. Maybe you can cut the flight times to Centauri of the Voyager probes from 60,000 years down to about 10,000 years. Still a rather long time. You have to bring a lot of science fiction from Bain just to keep you occupied for that and to keep you interested. Okay. Then we have the human factors. If I'm planning a trip, I like it to be, say, a couple of weeks trip. If I'm planning a 1,000-year trip, well, I'm not sure. It would have to be an extremely comfortable environment. You also have to deal with aspects of food. You've got to feed your people. Gravity, we have no idea what the minimum gravity is that humans can take. In fact, a lot of talk by Elon Musk and folks like that about colonizing Mars in 10 years. Man, we don't know that a woman or a female of any higher mammal can carry babies to term at 0.16 gravity on the moon or 0.38 gravity on Mars. And certainly, as Ken Roy has suggested in an earlier paper, we might be able to build a centrifuge for the women to live in. They might find that a little bit boring to spend 9 months in a centrifuge. Not only women, but mammals of other species we might take. I'm not sure my cats would like it, for instance. So, of course, we have a number of solutions to this. We have generation ships. We have artificial gravity by spinning them. We can have passive or active shielding. And actually, radiation shielding outside of the realm of the planets might be a lot better than radiation shielding within it, because if you're working with superconducting magnets, you don't need all of the coolant. So it might be a lot more effective, a lot better, a lot less massive. And of course, you might also have the concept of humans hibernating, although there have been a number of conferences, symposium, the Astra Symposium in northern Italy during the summers for many years, and medical doctors working with hibernation went there, and basically, ultimately, some of them said, listen, we're not squirrels. We don't hibernate. We would need extensive gene modification to do it. It's not impossible that we could do it, but we certainly can't do it now. And then other people have talked about the possibility of a singularity in which you upload human beings, the essence of a human being. I don't want to say the soul of a human being because that has too much baggage. The essence of a human being into a computer. But if you do that, what are you going to download when you get there? You know, are they going to have frozen bodies that they can re-inhabit? Maybe, but it seems a little strange to me. Anyway, the other type of obstacle are called great filters. Now, one of the great filters, of course, is nuclear war. We have less of a problem with that than we did in the past, but a couple of small states, as we know, are proliferating the nuclear weapon technology, and you don't know when stupidity could be taken to an extreme level. As long as we have so many bombs out there, this is a real problem and a real threat. Then we have climate change. Climate change is real. In fact, we all know it here because obviously, because of climate change, the Tennessee River has overflowed its banks. It reaches all the way to Kansas. So that's a demonstration right there. We have to deal, of course, with asteroid impacts and giant volcanoes. Asteroid impacts we can deal with. The dinosaurs couldn't. The hadrosaurs were not that advanced at the time. Well, maybe they were from a Star Trek episode, but they didn't apply it correctly. We could move asteroids. And I think I would like to see asteroid exploration and utilization worked with in a large way just to get us used to doing this. Giant volcanoes, we can't do a lot. And we know that there's one at the Yellowstone. There's another one in Italy, Naples. Naples is, and its surrounding environment is right over the caldera of Vesuvius. And once going to a conference in Capri, I had a chat with a woman who was on the ferry, who was a geologist, an Italian geologist, and says, what happens if Vesuvius blows with 2 million people on top of it? And in Italian fashion, she did this. And that just might be what would happen. Okay. We also have near supernova. Fortunately, the nearest stars that might go supernova right now, Betelgeuse or Rigel, are upwards of 500 or 600 light years away. So they would not have a major effect. But some civilizations might feel it. And then there's a possibility of berserker ET probes. A number of years ago, Les Johnson wrote a very interesting science fiction novel, which I encouraged him to do, Mission to Methone. How many people have read that? Okay, good. And you may going to sell some. Okay, good. And what he has, I'm not going to give the plot away, 2 races. One race is interested in preserving life, having consciousness develop in as many aspects as possible, many forms as possible. The other race is interested in being number one and wiping out the competition. So the interaction between these two is amazing. And of course the Berserker, I forget, anybody remember the name of the science fiction writer who came up with it? It wasn't David Brin, was it? Okay, thanks. Okay, and of course political dysfunction, which we've all heard a lot about, on both sides of the Atlantic. We don't have to talk more about that now. We get too much of it anyway. All right, what if we can overcome these? If we can overcome these, we have, last I saw, at least 4,000 extrasolar planets have been discovered and confirmed. There are thousands of others that TESS is discovering, which have not been confirmed. I've heard as many as 12,000. Many of these are in or near the habitable zone of their star, and also the habitable zone of the stars have been spreading, because we know that Europa, moon of Jupiter, could have life because of tidal effects, and Titan could have non-terrestrial type life also, and you can have situations, not only tidal effects, but tectonic effects on distant objects very far from their stars. So the habitable zone may well be spreading. On the first or second, I believe it was the first meeting of Breakthrough, I also am an advisor, like a few other people here, to Breakthrough Starshot. All of a sudden it came out that Proxima Centauri apparently has a 1.3 mass, Earth mass, 1.3 Earth mass planet in its habitable zone. And people have been arguing about the habitability of planets circling red dwarf stars. Many of them are getting a little more optimistic about it. But having one of these right in our backyard, the nearest star, indicates there's a lot out there. Okay, so and the classical habitable zone, as I mentioned, is expanding. So this is a very nice image from Hubble, and of course it's overexposed because Hubble doesn't like to look at stars that bright. These are the Alpha Centauri suns, which together have a visual magnitude of something like 0 to third or fourth brightest star in the sky. I don't know which of these is A and which is B. Does anybody know? Okay, nobody else does either. I don't feel so bad. Okay. And we know that they're both sun-like. A is a bit brighter, a bit hotter than the sun. B is a bit cooler. And they come as close, about as Saturn to the sun, about as far as Uranus and Neptune from the sun. There's a good chance that both of them have planets in the Hab zone. Okay. And we'll talk about the different modes of starflight. And these are things that have been suggested. Nuclear electric was the first to be suggested. That was by Les Shepard in 1940. I think 1952 his first paper came out. The problem with that is the specific mass of nuclear fission reactors has to go way down, by probably a couple of orders of magnitude, for it to get a ship to the stars within, say, 1,000 years. Then we have thermonuclear pulse, and this, of course, is Freeman Dyson, Ted Taylor's concept, Stanislaus Ulam, Project Orion, which came out of initially a Cold War effort to develop an interceptor to shoot down Russian nukes, much might be orbiting, and then became a backup to Apollo en route to the moon. And when Freeman Dyson did not like the fact that it had been canceled, he published in the October 1968 issue of Physics Today one of the most wonderful papers I've ever seen, really demonstrating that Orion could take human colony ships to the stars on flight durations of centuries to a millennium, using the nuclear arsenals of the then nuclear arsenals of the U.S. and the Soviet Union. This also evolved into things like Project Daedalus, British Interplanetary Society, and so on, which is a more restrained version in which instead of using bombs as your propulsion, you use devices, little fusion pellets, which are initiated by electron beams or laser beams. Finally, you have the antimatter rocket, which is lovely. It would be nice if we could do that. But to produce enough antimatter to do it is something that's well beyond us. One of my colleagues at New York City College of Technology is an Italian guy, Giovanni Assola, who spends some of his summers working at the CERN. When Dan Golden, the movie of Dan Golden's novel Angels and Demons came out, I asked him how long it would take if CERN was dedicated, if LHC were dedicated to produce 1/8 of a gram of antimatter to destroy the Vatican. He looked at me and said, be patient, about 100 million years. So we can't do it yet, although we might be able to use, as Mason, Peck, and a few others have talked about, anti-electrons to energize, to basically catalyze fusion reactions. That's a possibility. Then we have the solar photon sail. Using graphene sails, you can probably cut the flight time for a human habitat to go to the stars to about 1,000 years. You could do a lot better with a robotic ship. But humans, what really seems to be a problem for humans is we can take 3 gravities for an extended period of time, hours to days. We can't take much more than that. A robot can take thousands of gravities, as we know from Project Starshot. Okay, then we have the electromagnetic sail. You can also push against the solar wind using various approaches like this, the electromagnetic sail. The problem with this is you can't quite get as fast as with the solar photon sail because you're limited by the speed of the solar wind, the particulate wind. And finally, physics loopholes that we'll talk about in a little bit. Now here's the nuclear electric rocket. I'm not sure if this is argon or this is xenon. Usually it's better to have a noble gas as your exhaust because that way you can reduce basically chemical problems, erosion of certain types in the, I don't want to say combustion chamber, the accelerator grid. And this is Project Orion. This is the original one. It's not, the explosion behind it is probably an atomic bomb or a hydrogen bomb. That pusher plate that you see would be connected to the world's largest shock absorbers. And actually, Orion had a movie. It was in a movie, the movie Deep Impact. And it was an Orion ship because it was necessary to use a ship like that to interact with, to actually visit the comet that was approaching the Earth. Okay, here's Project Daedalus, which is a 2-stage vehicle. And it is basically making use there of helium-3, probably mined from the upper atmosphere of Jupiter, which would be a nice trick if we could do it. Some people say we could get it from the lunar regolith, but that's really not proven. We have to do a lot more lunar mining to see if that's feasible. And Project Daedalus would get a probe to Alpha Centauri or so within a bit less than a century. Okay, matter-antimatter annihilation rockets could be a lot faster, of course, assuming that we could produce antimatter in quantities, store it, and keep it out of the hands of terrorists. And this is, of course, the solar photon sail. And when I looked at a beryllium sail with my former department chair and colleague, Roman Kesavich-Valley, we demonstrated about 2,000 years to Alpha Centauri. And of course, you can cut that down to 1,000 years with graphene. You have to learn how to produce graphene in quantity, which is hard today, but certainly not impossible. And how to deposit this on as a thin film sail in space without having your structure getting blown out of the solar system before you're ready for it. Okay. This is an electric magnetic sail. I don't know particularly which one this is because I took this off the web because it's pretty. But you can see that the electric field there is basically reflecting protons from the solar wind. The solar wind is emanating from the sun in the lower left. Okay. And here's beamed interstellar propulsion. This was thought up initially by Bob Forward and Philip Norum, I think, might have come a little bit before Bob. And basically, this is his initial concept, which also was featured in Buzz Aldrin's science fiction novel with John Barnes that I consulted on, Encounter with Tiber. You would basically need a position control system on the solar-powered laser, which is amazing because you have to impact a sail, which might be a 4-stage sail, at distances of trillions of kilometers. Not an easy trick. I asked once a NASA engineer during my stints at Marshall if we had any technology that could do this, and his eyes sort of glazed over. So, not easy. Now this is Project Starshot, and this was initially a concept of the physicist Phil Lubin, and he interested a funder, a billionaire philanthropist, Yuri Miner, and basically you would take and this is one of those things that I work as an advisor on, you would have to take a 50 to 100 gigawatt laser array, probably fiber lasers, put on a mountaintop in a southern country such as a Chilean volcano, beam that against something the size of a piece of paper without melting that piece of paper, and the paper has to be appropriately shaped in some way. Not a piece of paper, of course, it's a sail, to stay in the beam for a period of minutes without being blown out of it completely. And, accelerating at 5 or 10,000 gravity to 20% the speed of light. And then you have to shift the orientation of the sail so that it's end on rather than flat surface on into the interstellar medium. So at 20% the speed of light, you don't want to be too eroded, which you would be by interstellar dust. And then when it gets to Alpha Centauri, or Proxima Centauri, it has to unfurl. And what it does, not unfurl, has to change its orientation again, facing the Earth. And somehow it has to do good science, which might be a little hard for something with a mass of a gram, and beam that information back to the Earth. And when you talk to people in space science about this, they're a little leery. Like I gave a talk with Claudio Marcone once on sending sail probes to the gravity focus of the sun. We gave it at Cornell, and in the second row was Carl Sagan eating a pastrami sandwich. And the best we could do at the time was a 50-year trip to the gravity focus of the sun. And what Carl said, and he was absolutely right, is, okay, you launch this tomorrow. In 50 years, there'll be so many advances in earthbound and spacebound astronomy that what you send out towards the gravity focus at 550 AU will be completely obsolete. And it was an interesting point, and when you talk about breakthrough, we have to consider things like that also. But there's a wonderful, Ken Parkin, who is here, has wonderful papers in Acta Astronautica and maybe also JBIS too, I forget. Is it in JBIS also? Just Acta, in which you can get in there and you can manipulate the various parameters that go into the Starshot system. And you can try to see what you come up with. It's quite a challenge. Okay. And this is one of the things which has come out of it. This is a sprite. And basically it has been worked on by Zach Manchester and Mason Peck. Zach is at Stanford, Mason's at Cornell. And basically you can take a large spacecraft and pico-miniaturize it so it fits on a little chip. And that's an interesting trick that you can do. That is one thing which is built into Project Starshot. So we'll continue. Here are the various issues of it. One of them, the one that I've had a lot of fun with, is the necessity for a curved sail. Now, you must have a sail which either a conical shape or a spherical shape to keep it inside the beam for 2 or 3 minutes. The beam is moving because one side of it, the terminus is facing the Centauri system, the other side is on the mountaintop. But then how do you keep this curved structure there so that, it can withstand 10,000 gravities? And for this, my wife, C. Bangs, the artist who has worked a lot with holography, and her holographer suggested a good solution to me and the other people at breakthrough that maybe what you can do is have a holographic, or as Grover Schwartzlander would say, a diffractive sail, something that the photons think is curved, but from the point of view of inertia is flat, so it ain't going to collapse. Brilliant idea. I wish I had thought of it. Okay, we'll continue. Generation ships. This is one of the O'Neill colonies. And, this might be a comfortable way of living. If you could put a small group of people, you can keep the ecology closed, keep leakage down, keep it going for 1,000 years. And finally, you might want to consider transhumans. If we live in far distant space colonies, I don't want to say space colony, that's no longer good, a far distant space habitat. That's the politically correct way of saying it. You have a lot of choices, radiation levels, magnetic fields, your gravity. You might change humanity. Even when they spend a few months or a year in space, astronauts begin to see changes to their bodies. Over a generation or two, we might develop things which aren't human from our point of view. They'd be considered transhumans. And all of these things can be varied as we desire. And also, ultimately, we might become ET. We might become the extraterrestrials. We might spread through the galaxy in these things. But none of us here are going to be the ones doing it unless something else happens. And the something else is wildcards. Now, I've been at conferences where these things have been discussed, and Sonny White, Heidi Fern, John Woodward, they put together these ideas. And my own approach is skeptically optimistic. I hope we find a loophole. We found a loophole before. Nuclear fission was found as a loophole in nature. In 1937, a year before Lisa Meitner, Otto Hahn, Otto Strauss's famous paper, some of the real top-notch experts in physics were quite convinced and said publicly that we'll never have nuclear energy. They were wrong. There might be some type of loophole that has been found or will be found at some point in the not-too-distant future, and this might be one of them. This is the EM drive. The first time I heard of the EM drive was at one of the Astra conferences, or it might have been an IAC with David Fern, the late David Fern. How many people knew David? A few did, good. He was a wonderful guy. He was a UK, maybe you no longer can say UK English, you have to say, because we don't know if the UK will continue to exist, getting back to political dysfunction. But okay. He was a nuclear engineer, and basically he'd been approached by Robert Scheuer, and he tested this thing, and yes, he was seeming to get a measurable thrust. And I went through the numbers and said, yeah, you're getting a thrust, but it obviously violates conservation of linear momentum. And he agreed. And some people, like Mark Millis, sitting here, who has analyzed a lot of the breakthrough ideas for NASA, have come up in, I believe, the Centauri Dreams blog. He presented all of the different things that you have to overcome with these devices to make them work. Now, right now, it's unclear if they work at all. But I would say, loopholes in physics have been found before. We should realize it's possible that there might be another one. What I would like to see, though, is if you're working, anybody here working on a loophole project right now? Nobody in this audience. Okay, we all have sailors and nuclear people and folks like that. If you know anybody who's doing it, I would suggest you have to test it in the space environment to demonstrate that it works. A CubeSat is expensive. A CubeSat's $300,000 to $1 million. But one of the sister campuses to mine, which is New York City College of Technology, part of the City University of New York, is Medgar Evers College. And they have an arrangement with a NASA center in Palestine, Texas. Anybody know that facility? Okay, Palestine, Texas is a place where they launch stratospheric balloons. It should be possible for a fraction of the $300,000 to $1 million price tag to test something hanging from a balloon at 100,000 feet or 120,000 feet just to see if you get something. Okay, continue. And basically, if we get through the great filters, our probes are going to venture to the stars. And in the farther future, we may well follow. And if we have a space drive, if something like this can actually be made to work, it may happen a lot sooner than we think. Okay, thank you. I have time for questions.
A comment and a question. You are suggesting that the best test method for advanced alternate propulsion would probably be CubeSats or orbital experiments. I just want to point out the difficulty with this is on the surface of Earth, you can get really incredibly good measurement technology to bear on thrust measurements. Mm-hmm. When you get into orbit, you have really crappy measurement technology. Yeah. CubeSats are very, very crude, crude objects. So the difficulty of separating out all of the other perturbations, all the other possible effects, all the electromagnetic perturbations. Remember, in general, all of these devices, if you took the power and took a small percentage of that power and emitted it as photons, you would more thrust than the actual thrust. So suggestion is probably that's a backward statement. Probably you can't get good enough measurement technology on a small sat and a CubeSat in order to get a good measurement. You have to do the measurement on Earth where you can get really good technology for the thrust.
Okay, thanks, Jeff. I think that's an excellent comment. I didn't mean to say that you negate the terrestrial measurements. But what I said is if you can demonstrate thrust and actually visually show it, you will possibly advance the technology readiness level of these devices by testing it in space. Just as a supplement, yeah. Okay.
So you mentioned phase coherence of diode lasers. Has that been demonstrated on any large scale?
Okay. The fiber laser, and I just checked this recently, I think the largest one is about 1,000 kilowatts, if that's correct. Now, if you need 50 gigawatts, you need more than 1 million of these. The problem, of course, is phasing 1 million or more lasers to hit the same thing. What is your reliability? What happens if one of them or many of them malfunction? Are you going to have interesting vibration effects or torque effects on your tiny little sail? All I can say about this is, hey, I look at the sail. I don't look at the laser. As the old song about Werner von Braun goes, that's not my department. I don't know if there was an answer to it, but we were all told as breakthrough advisors, don't say it's impossible. Say it's very, very, very challenging, which it is. Yeah, let's.
Greg, your career has spanned since really the burgeoning of the field, when a lot of the original
I started
papers,
at the age of 3. That's
yeah,
right.
you did. But when a lot of the original, the seminal papers on a lot of these propulsion technologies were written, you've written the Starflight Handbook. Which of the technologies in your professional career do you think has advanced the fastest or the furthest? Which is making progress, in your opinion?
I think the sail. And that is not because of physics or anything like that. That's because of politics. We can test small sails unfurled from CubeSats in space for a cost in the millions of dollars or tens of millions of dollars. We can't easily test in current politics a fission or fusion pulse device. If we tried to, I know a couple of years ago, the Chinese said, no matter what America or Russia does, we are going to keep our nuclear arsenals in case we have to shoot down any errant asteroids. They got a lot of flack for that. So certainly it would be very hard to do that. It's, it's quite possible, but we have to be able to test these things in space.
Let's thank our speaker.
Thank you. Thank you.